All right, suppose you have a stretched string of mass m and length L, and it's stretched between two supports, and the tension in the string is T. Notice that this is the same tension that we've been talking about this entire time. So you have the string that's stretched, and so there are two tension forces at the two ends of the string and throughout the string. So the tension force is T. We are interested in finding out the speed of waves on the string. So there's many ways in which you can create waves in the string. You can shake one end of the string, or you can pluck the string somewhere, or you can strike the string somewhere. So there's multiple ways you can produce waves on the string. We want to find out what is the speed of the waves on the string. So the speed of waves on a string is given by the following expression. V is equal to the square root of T divided by the mass per unit length of the string. And this quantity, mass per unit length, is sometimes called the linear density. So you can also write this formula more compactly as square root of T divided by mu, where mu is nothing but the mass over the length of the string, or the linear density of the string. So this is a useful formula. It gives you the velocity of waves in a stretched string. So you can see that the velocity would be higher if the tension were higher, which is probably something that you noticed when you did the wave simulation quiz. If you increase the tension, the velocity of the waves is higher. And also, the velocity is inversely proportional to the linear density. So if you have a very thick string where the mass per unit length is large, the velocity will be small. Whereas if you have a thin string or a thin wire where the mass per unit length is smaller, the velocity will be higher. So that's it. All right, let's do an example problem on this. So please pause the video for a moment and see if you can work this out on your own. So this problem is saying that you have a wire of a certain length and mass that's under tension, and there is a wave that's propagating through this wire, and you're given some information about the wave. You're given the frequency of the wave, the wavelength, and the amplitude. And the first part of the question is asking for the tension in the wire. So what is the tension going to be? Well, let's see what we can figure out. So we have the mass and the length, right, of the wire, and we also have the frequency and the wavelength of the wave that's propagating through the wire. So can we find the velocity of the wave that's propagating through the wire? Yes. So the velocity of the wave is going to be f multiplied by lambda. I'm just going to work in letters and not plugging any numbers. And so once we have the velocity, we can use our new formula for the velocity of waves in stretched strings to find the tension. So the tension would simply be V would be equal to T divided by mu, which is mass divided by length. And so from here you can just solve for T. All right, and that takes care of the first part. For the second part, it's saying that what is the velocity of the sound wave that would be produced in air as a result of this vibrating string. So this could be a guitar string that's vibrating, or the string of any musical instrument. And as this string vibrates, what happens is that the air molecules next to the string are also set in motion. So the air molecules will vibrate as well. And those vibrating air molecules will pass on their vibrations to their neighbors. So the neighboring set of air molecules will vibrate as well, and they will pass on their vibrations to their neighbors, and so on. So you will have a wave propagating through the air as well. This kind of wave is called a sound wave, which we'll study in chapter 16. So the question is asking, what is the wavelength of the sound wave that would be produced in air as a result of this vibrating string? So to answer this question, you have to remember one important property of waves, which is that when a wave travels from one medium to another, the frequency always stays the same. The wavelength and speed of the wave might change, but the frequency always stays the same. So keeping in mind that frequency will remain the same, can we find the wavelength of the sound waves? So we can just use this formula V is equal to F lambda, which is true for all waves. The V would simply be the speed of sound, so Vs. The frequency will not change, so it's going to be the same frequency as the frequency of the wave on the wire. So it's going to be 450 Hertz multiplied by the unknown wavelength of the sound wave. And so from here you can solve for the sound wave wavelength. All right, the next thing that we are going to talk about is interference. Now, in a medium, there is no reason why only one wave should propagate. You can have multiple waves propagating through the same medium at the same time. So to give you a very simple example, suppose let's just stick with our waves on a string example. So suppose there is a long string and you are holding on to one end of the string and shaking it, and you're creating a wave that's traveling to the right. All right, now let's say at the other end of the very long string, your friend is holding the end of the string, this end of the string, and shaking it and creating a wave that's traveling in this direction, like that. Your wave is represented by y1 and your friend's wave from the right is represented by y2. Now eventually these two waves will merge and overlap. The overlapping of waves in the same medium is called interference. So the interference is the phenomenon where multiple waves overlap in the same medium, or multiple waves traveling through the same medium overlap in a certain region. That phenomenon is called interference. So when these two waves in our example overlap, what is the resulting y going to be? Remember that y represents the displacement of any particle. So if this is the equilibrium position, y is this displacement of this particular particle. The displacement of this particle is this y. The displacement of this particle is this y, right? So y is the displacement of each particle. So in the region where the waves overlap, how do we find the resulting displacement? The answer is very simple. To find the resulting displacement, you simply add up the displacements that would have been caused by each wave individually. So if the only wave in the medium was your wave, y1, then y1 would represent the displacement of any particle in the medium. And if the only wave in the medium was the one caused by your friend, y2, then y2 would have represented the displacement of any particle in the medium. When both waves are present, the resulting displacement is simply the algebraic sum of the displacements of the waves produced by of the individual waves. And this beautiful result, the fact that you can simply add up the displacements of the two waves, of the waves that are overlapping to get the resulting displacement, is called the principle of superposition. And it makes our lives really simple because we can just use algebraic addition and subtraction to find the resulting displacement when you know the displacements that would have been caused by each individual wave. All right, now let's look at a couple of special cases of interference. So suppose you have two waves. They're represented, let's focus on this diagram on the left. Suppose you've got two waves. One of them is represented by the red pattern and the other one is represented by the blue pattern, and these two waves are passing through the medium, which is the same string here, and these two waves are exactly overlapping each other. So they are identical and they're exactly overlapping each other. What is the resulting y going to be? Consider the particle that lives at this distance over here. If only the red wave was passing through the medium, its displacement would have been y2. And if only the blue wave were passing through the medium, its displacement would have been y1. So when both the waves pass through the medium, this particle is feeling forces from both of these waves simultaneously, and so it will have a displacement which is twice which is the sum of the displacements of y1 and y2, sum of the displacements of the two waves. So the resulting displacement is y1 plus y2. And so you have a large displacement, right? In other words, the two waves are reinforcing each other. The same thing would be true for a point that's over here. The blue wave would have sent it downwards, and the red wave also wants to send it downwards. And so both of these reinforce each other. I mean, the two waves reinforce each other. And again, you have this large displacement over here. So this is called constructive interference, where the waves always reinforce each other. So this is constructive interference. Now, let's look at the opposite situation. Here you have the blue wave and the red wave, but you can see that they're perfectly out of sync. So if you consider a particle over here, the blue wave would have sent it all the way to the top, whereas the red wave wants to send it all the way to the bottom. So here the waves completely, the effects of the two waves completely cancel out over here. Every point, each wave is trying to make it, the two waves are trying to make it do completely opposite things at every point. And as a result of that, their effects completely cancel out, and you have no wave at all. As you can see, the medium is not moving at all, because the waves completely cancel each other out. So this is called destructive interference, where the waves are exactly out of phase. So they just cancel each other out, and there is absolutely no effect on the medium at all. It's as if there is no wave at all. Finally, here is a situation which is more common. Here you have the two waves not exactly in phase, neither exactly out of phase. So in some places the two waves reinforce each other. In other places the waves cancel each other out. So the places where the waves reinforce each other, you would get a strong, you would get a large displacement. And the places where the waves cancel each other out, you would get a smaller displacement, not necessarily zero, because they might not exactly cancel each other out. So you get a wave like this, which is basically an intermediate result. So you have neither perfect reinforcement nor perfect cancellation. And so this is the more common situation.